like a half, actually become a quarter when you square them, and that becomes 16, and so on. But then numbers much less than 1, like
Today, I'd like to tell you about a piece of math known as holomorphic dynamics. This is the field which studies things like the Mandelbrot set, and in fact, one of my main goals today is to show you how this iconic shape, the poster child of math, pops up in a more general way than the initial definition might suggest. Now, this field is also intimately tied to what we talked about in the last video with Newton's fractal, and another goal of ours towards the end of this video will be to help tie up some of the loose ends that we had there. So first of all, this word holomorphic might seem a little weird. It refers to functions that have complex number inputs and complex number outputs, and which you can also take a derivative of. Basically what it means to have a derivative in this context is that when you zoom in to how the function behaves near a given point, to the point and its neighbors, it looks roughly like scaling and rotating, like multiplying by some complex constant. We'll talk more about that in just a bit, but for now, know that it includes most of the ordinary functions that you could write down, things like polynomials, exponentials, trig functions, all of that. The relevant dynamics in the title here comes from asking what happens when you repeatedly apply one of these functions over and over, in the sense of evaluating on some input, then evaluating the same function on whatever you just got out, and then doing that again, and again, and again, and again. Sometimes the pattern of points emerging from this gets trapped in a cycle. Other times, the sequence will just approach some kind of limiting point. Or maybe the sequence gets bigger and bigger and it flies off to infinity, which mathematicians also kind of think of as approaching a limit point, just the point at infinity. And other times still, they have no pattern at all, and they behave chaotically. What's surprising is that for all sorts of functions that you might write down, when you try to do something to visualize when these different possible behaviors arise, it often results in some insanely intricate fractal pattern. Those of you who watched the last video have already seen one neat example of this. There's this algorithm called Newton's method, which finds the root of some polynomial p, and the way it works is to basically repeatedly iterate the expression x minus p of x divided by p prime of x, p prime being the derivative. When your initial seed value is in the loose vicinity of a root to that polynomial, a value where p of x equals 0, this procedure produces a sequence of values that really quickly converges to that root. This is what makes it a useful algorithm in practice. But then we tried to do this in the complex plane, looking at the many possible seed values and asking which root in the complex plane each one of these seed values might end up on. Then we associated a color with each one of the roots, and then colored each pixel of the plane based on which root a seed value starting at that pixel would ultimately land on. The results we got were some of these insanely intricate pictures, with these rough fractal boundaries between the colors. Now in this example, if you look at the function that we're actually iterating, say for some specific choice of a polynomial, like z cubed minus 1, you can rewrite the whole expression to look like one polynomial divided by another. Mathematicians call these kinds of functions rational functions. And if you forget the fact that this arose from Newton's method, you could reasonably ask what happens when you iterate any other rational function. And in fact, this is exactly what the mathematicians Pierre Fatou and Gaston Julia did in the years immediately following World War I. And they built up a surprisingly rich theory of what happens when you iterate these rational functions, which is particularly impressive given that they had no computers to visualize any of this the way that you and I can. Now remember those two names, they'll come up a bit later. By far, the most popularized example of a rational function that you might study like this, and the fractals that can ensue, is one of the simplest functions, z squared plus c, where c is some constant. I'm going to guess that this is at least somewhat familiar to many of you, but it certainly doesn't hurt to quickly summarize the story here, since it can help set the stage for what comes later. For this game, we're going to think of c as a value that can be changed, and it'll be visible as this movable yellow dot. For the actual iterative process, we will always start with an initial value of z equals 0. So after iterating this function once, doing z squared plus c, you get c. If you iterate a second time, plugging in that value to the function, you get c squared plus c. And as I change around the value c here, you can kind of see how the second value moves in lockstep. Then we can plug in that second value to get z3, and that third value to get z4, and continue on like this, visualizing our chain of values. So if I keep doing this many different times for the first many values, for some choices of c, this process remains bounded. You can still see it all on the screen. And other times, it looks like it blows up, and you can actually show that if it gets as big as 2, it'll blow up to infinity. If you color the points of the plane where it stays bounded black, and you assign some other gradient of colors to the divergent values based on how quickly the process rushes off to infinity, you get one of the most iconic images in all of math, the Mandelbrot set. Now, this interactive dots and stick visualization of the trajectory